Hey guys, we're going to be discussing applications of differential equations in this session. So here we go. I guess there's some key points that you kind of need to know for applications of differential equations. Kind of like what we did for our optimization. You know how there was like that 7 steps that I gave you guys? Very similar to this in applications as well. The first thing is solve the equation and have constant as a part of your solution. So this is like the general equations. Now the second part is use the information that's given to you and then come up with a particular solution. That's what I kind of say here. And finally, the third part is use the particular solution to actually answer the question, because that's what they normally do. Okay, so these are the 3 things you need to remember. So with applications is come up with a general solution, then come up with a particular solution, and then solve the problem itself. Now just to recap some of the types of differential equations that you've actually seen so far. Now the first one was when the quantity is changing at a steady rate. That was the first one that you had to look at, the first type of differential equation. The second one was a rate of change of quantity is some function of time. Then the third one was where the quantity is proportional to the quantity itself. And finally, the last type of differential equation was when a differential equation has separate variables. So these are some of the 4 types that you might would have seen in the last few exercises. So with the first one, if you remember, this was when dy dt equals k, so y is equal to integral of k dt. And when it's the second situation, when a rate of change of quantity is some function of time, sorry, let me just write this as kt plus c, then you would have dy dt equals some function of time, which means y is equal to integral of f of t dt. And the third situation, dy dt equals ky. So we know that we can integrate this as 1 over y dy equals k dt. Sorry about the little tiny space management here, but just got to deal with it at the moment. Integral of 1 over y dy equals integral of k dt. And simplifying this, we get ln of ay equals kt, which is just y equals bekt. Now you might wonder where did a and b come from? But like I said before in my previous videos, it's just a constant, and it's just they're all written in different areas, so they all mean the same thing, but just can't use the same letters for them, because if we use ln of a, so imagine b as what am I saying? Imagine b as just e to the power of ln of a. No, not to e to the power of ln of a. Anyway, look, it'll make sense in the next example. I'll actually show you guys how to do this in one of the examples, and it'll make sense. All right, and the final bit was with this one is separate the variables and then integrate. So anyway, going back to the third, the one where it's proportional to the quantity itself, I'll actually do an example in the next couple of slides, and hopefully we'll get the hang of it. Alright, so this is the example I want to have a look at. A new car is purchased for $30,000. During the next 10 years, the rate of change in the value of the car is given by the differential equation dx over dt equals negative kx, where x is the value of the car after t years and k is a constant. After 10 years, the car is expected to have a scrap value of $100. Find the value of the car when it's 4 years old. Okay, so that's our differential equation right there. We have dx dt equals negative kx. So remember, we need to come up with a general solution first, and then a particular solution, and then solve the problem. So the first step we're going to do is come up with a general solution. So this could be written as 1 over x dx equals negative k dt. And we need to integrate both sides. So when we integrate the left-hand side, we're going to get ln of cx, which equals negative kt. Now, remember in the last one we had the a and b? I'm going to show you guys how it actually changes around. So we can write cx is equal to e of negative kt. Now, what we can then do is we can write this as x is equal to ae negative kt. Now, you might be wondering, well, what happened to the c? But just imagine like this. A, because c is a constant. Because c is a constant, if I do 1 divided by a constant, it'll be another constant. So a is just another constant. That's what I was trying to say earlier, but it was a bit tricky with that space there. Okay, so once we've done this, this is our general equation at the moment. X is equal to ae negative kt. Well, general solution. Now we need to find the particular one. And I guess we go into the purple box for that. A new car is purchased for $30,000. So we know that t is equal to 0 when x is equal to 30,000. So we can write this formula down. And we know that 30,000 equals ae negative k times 0. So rearranging everything here, we're going to get 30,000 equals a times e to the power of 0. Now e to the power of 0 is equal to 1. So we can say that a is equal to 30,000. So if a equals 30,000, we've got x is equal to 30,000 e to the power of negative kt. Now unfortunately, we still haven't found the particular solution because k is still a variable that we need to figure out. And to do that, I'm going to go into the next slide, guys, and work from there. So that's still my question there. So what I've got is so far is x is equal to 30,000 e negative kt. Now see how it says in the green box, after 10 years the car is expected to have a scrap value of $100. So this means when t is equal to 10, x is equal to 100. So now I can substitute this in the equation and figure out what k is. So if x equals to 30,000 e of negative kt, then I can say 100 is equal to 30,000 e of negative k multiplied by 10. Rearranging this, I get 100 divided by 30,000 equals negative 10k. So 1 over 300 equals e to the power of negative 10k. So using log rules, I can say ln of 1 over 300 is equal to ln of e to the power of negative 10k. Now ln and e, it's just basically cancel out each other. So I got ln of 1 over 300 equals negative 10k. So which means k is equal to ln of 1 over 300 divided by negative 10. And it simplifies to 0.703. Sorry, 0.5703. So k is equal to that. So because k equals this, now I finally have my equation, which is my particular solution. X is equal to 30,000 e to the power of negative 0.5703 t. So all this in the green box, I actually had to use that green box information from the question itself to figure out the particular solution. Now once I have this, I can go find the value of the car when it's 4 years old. Because for this, t is equal to 4, and I'm trying to figure out what x is. So if x equals 30,000 e negative 0.5703 t, I just need to substitute t as 4. And when I do this, I end up with $3,064. And I finally answered the question. So as you can see, guys, there were a lot of things we need to do in this, but the first thing is find the general solution. The second thing is find the particular solution. And the third thing is answer the question itself. Now, if in the previous slide I showed you guys how to get to the general solution, And then in this slide, I've worked with a particular solution in the green box, and finally solved the question in the red box here. All right. Okay, that's basically it from this session. Thank you for watching, guys.